Today we will be taking a look at a dodgy USB charger. So I know for certain that this is dodgy because I have already taken a peek inside of it. Uh, but I'm going to show you how I initially figured out that this could be dodgy before taking a peek inside of it. So first of all, this thing feels very light in my hand, and if I get a scale, and I'm gonna weigh it, it says 20.4 grams. And let's compare this to a charger with a similar size and shape, which is actually a little bit smaller in all three dimensions. And despite this thing being smaller, it weighs 25 grams. And I should also mention this charger was made by Amazon, and it has UL listings. This one doesn't have labels anywhere except for on the side here, where it just says travel charger and some specifications and made in China. So you don't really know what you're dealing with when you're handling this thing. So those are just two simple signs of how to find a dodgy USB charger. So first of all, the way that I took a peek inside this was that I actually managed to jam tweezers into this little gap right here by the plug, and let me go ahead and get those tweezers. These are very sharp so they can fit into tight spaces, and I just put them in here, and boop! The plug comes off easily. And inside we have a very tiny circuit board. Well, I mean, it takes up the entire inside of this case, but it's very low profile. So what we have here is, of course, the inputs over here. Let's go to the bottom. They go directly into the bridge rectifier. Let me get a more suitable pointer tool. They go directly into the bridge rectifier without any sort of interference suppression, no fuse, not even a thin track on the board. And then out of this, they just go into the rest of the switching circuitry. And, well, of course, directly after the bridge rectifier, there's a smoothing capacitor, which is 2.2 microfarads, which seems quite small for a 1 amp charger. Then, of course, there's a small auxiliary capacitor for delivering power to the chip, which is 4.7 micro, 50 volts. And then there is an interference suppression capacitor to reduce the amount of interference getting to the output. And this is supposed to be a Class Y capacitor, which is rated to handle high voltages, not necessarily because it will be having a high voltage across it during normal operation, but to minimize the risk of it failing short circuit. It actually says CY on the board, Class Y or capacitor Y, but if I slightly bend this thing out of the way and maybe bend the capacitor a bit too, it's just a regular 1 kilovolt blue capacitor, if you can just barely see. 102, which means 1 nanofarad, and 1 kV, 1 kilovolt. So it is not a proper Class Y capacitor and is more likely to fail short circuits than a proper Class Y capacitor. And don't even get me started on this transformer because it's a very low profile transformer. It doesn't have, the secondary wires do not have insulation on them. And it's probably going to be an absolute disaster inside of here, but we'll take a look at that later. And then there's the USB port, which isn't really the best quality. Let's look on the other side. So you can see the isolation distance between the primary and secondary side is not that big. Where are my fancy calipers? Let's measure the isolation distance. This is the closest point, and it appears to be approximately 1.5 millimeters on the board. There is a slot right here, so they did try to prevent stuff like carbon tracking from happening, but it doesn't even go all the way across this narrowest point, so it doesn't really make much of a difference. That is not good because carbon tracking is just where you can have high voltages that get little carbon traces to form on the board, and that can bridge the primary side to the secondary side. And in fact, this little trace right here is one of the terminals that's connected directly to the rectified mains, and this terminal right here goes directly into the Schottky diode, and the other side is connected directly to this USB port, which is exposed, and you could potentially touch it, which is not good. And also, the soldering quality isn't really the best. These two solder joints right here have giant holes in them, and this little leg of the capacitor looks like it got barely any solder on it, so this could potentially fall off and become a cold solder joint or something like that. Anyway, let's go ahead and desolder this transformer, because you can't look inside of a transformer without absolutely destroying it. So let's go ahead and fire up that soldering iron and get to investigating. So the transformer is desoldered, and the funny thing is that there used to be two pins right here which are actually connected to wires, but those two pins somehow managed to stay in the board. I mean, it's not like I desoldered this the best way possible, but I really have a feeling that they could have used a better sort of transformer bobbin to wind this thing across. Well, first of all, we are going to have to separate the ferrite core. So let's go ahead and remove this little bit of tape. Well, this might take a while. That's better. Now, we need to separate the core so that we can get access to the transformer bobbin, to remove the tape around it and unwind the sets of wires, but I don't want to bother heating this thing up with a hair dryer to open the core cleanly, so I'm just gonna crack it open. Ouch. The other side. Okay, that is, well, some of this stuff didn't even stay in the, oh my goodness, this is terrible. Would you look at that? This thick wire right here, the secondary, appears to be wound. Oh my goodness, why don't you focus on the foreground, Mr. Camera? Well, my goodness gracious. Okay, maybe now it'll autofocus. Okay, so this wire right here, which is the secondary, is wound directly below the auxiliary winding or feedback winding, which carries power to the chip and also allows the chip to change the duty cycle of the switching power supply to adjust for changes in the output load. And since they're wound directly on top of each other, and the feedback or auxiliary winding is touching the secondary winding, and the feedback winding has reference to mains voltage, then if the super thin lacquer on the wire were to fail, and well, then the mains voltage could get to the output and shock you. So that is not good whatsoever. The funny thing is that I actually do see some tape between the secondary and the primary, but that makes absolutely no difference, as the auxiliary is also referenced to mains voltage. And I mean, I don't really think you care about the number of turns in each part of the winding of the transformers, and this video is probably getting pretty long, so I will stop it right there.